All right, to pick up where we left off for lesson one, I'm just going to go back over our exponent laws really quick here, just as a recap, and then we'll move into today's lesson, which is working with rational exponents, okay, and then converting them to what's called radicals, and then converting them back to rational exponents. So we're going to be able to go back and forth. And remember, when I say rational exponents, I mean exponents that are fractions. Okay, so far we've only dealt with exponents that are whole numbers. We could also deal with exponents that are fractions. All right, and we're going to see how to evaluate them or solve them without even really picking up a calculator. Okay, so let's recap the exponent rules. When we multiply the same base, we can add the exponents. So the rule is a to the power of m plus n. When you're dividing the same base, you subtract the exponents. So to write it as a single power, you write it as a single a to the power of m minus n. Power to power law, you actually multiply the exponents. So you write it as an a and then an m times n. And if you ever see me use that dot just represents multiplication. Okay, so m times n. Anything to the power of 0, so any number or any variable. Remember, a variable just represents a number. So anything to the power of 0 just equals 1. And I proved it to you yesterday. You just need to remember it for sure, but I mean, it's good to understand why it equals 1 as well. If you have a base to the power of a negative variable or a negative number, okay, you just have to remember that you flip that. So remember that this is over 1 and that you would be flipping it to turn that m into a positive exponent. So it becomes 1 over a to the power of m. Okay, in this case, you have power to power law. So this negative m applies to the a and the b inside these brackets. So you get something like this, right? And so what you would do in that case, because they're both negative exponents, you would flip each of them and they'd both become positive exponents. So the a to the power of negative m, you would bring to the denominator and it would become a to the positive m. The b to the negative m, you bring to the numerator and it will become positive as well. So when you flip these back and forth, you're toggling between positive and negative exponents. So what this ends up equaling is this. Okay? All right, let's dive into just a quick recap before we start this new lesson here. So I just wanted to remind you of these root brackets, okay? And I'm going to just take you through a little bit, familiarizing yourself with these root brackets. Okay, these are called in math, they're called radicals. So whenever you see a value or a variable with a root bracket, they're called radicals. All right. If you see just your regular root bracket with no number, so let's say if I were to write this, I think we all know that this means square root. Okay. But what's not shown there, and remember, like, we're saying the word square root, and what's not shown there, because it's understood that it's the square root bracket, what's not shown is the fact that this is really written like this. It's the square root of a number. And so you put this little 2 in the top left corner. But because we understand that that's just the square root bracket, we don't ever show that 2, but it does exist there. Whenever we see a root bracket like this with no number in the corner, it actually means that that number there is 2 because it's a square root bracket. And so if you see something with a 3, that's called a third root, right? If you see something with a 4 in the corner, that's called a fourth root. And let's think of what that means here. Now, the square root means, right? So the definition of square root is you're kind of thinking what number times itself equals whatever's inside the root bracket. So for example, okay, let's say the square root of 9, right? So remember that 2 really exists there, even though we don't show it, but that 2's there. The square root of 9. You're thinking of what number times itself, and now because it's square root, so it's times itself 2 times, equals 9. That's the question you ask yourself when you see a square root bracket, right? You're saying to yourself, okay, it's wanting me to find out what number times itself 2 times equals 9. And in this case, we know, of course, that it equals 3. Okay? So that means then, let me do just, and I'll erase this because we'll write that out in a second. If you have a cubed root of, let's say, 27, in this case, you're asking yourself, what number times itself 3 times equals 27? All right, that's the question you're asking yourself. So let's fill in this box here, and I'm going to ask you to use your calculators here because I'm going to prove to you that the square root of 4 and 4 to the power of 1/2 mean the exact same thing. All right, so you're going to get the same answer. So you can pull out your calculators, find your square root button, and do the square root of 4, and you'll find that that equals 2, right? It's what number times itself 2 times equals 4. Well, it's 2 because 2 times 2 equals 4. If you pulled out your calculator right now and you did 4 to the power of brackets 1 divided by 2, close bracket, you would also get 2. Square root of 9 is 3. Pull out your calculator, do 9 to the power of 1/2, and you'll also get 3. So they're equivalent. Whether I show it as a square root or as to the power of 1/2, they actually mean the exact same thing, okay, mathematically. Square root of 16 is 4. 16 to the power of 1/2, you'll find, is also 4. Okay? So I'm just going to erase this here, and let's write out a conclusion. Okay, so our conclusion is that the square root of a value is equivalent to that value raised to the power of 1/2. Okay, now remember, that's for square root. So for square root, it's the same as raising to the power of 1/2. Let's see the cubed root now. So let's move on and let's take a look at the cubed root, and let's see if we get the same pattern here. So the cubed root of 8, by the way, in your calculator, if you're looking for cubed root, different calculators, some calculators may actually have a cubed root button. Some calculators might have something with a little X and then the root bracket. Okay, so I think it'll be either one of these buttons on your calculator to do cubed root. So basically, you'd have to put in a 3 for X. So you'd have to type 3 in your calculator, then press this button, and then put the number that's inside here. Okay, but some calculators have different orders of things, so you've got to play around with your calculator to make sure that you can do this. So the cubed root of 8 is what number times itself 3 times equals 8? It's 2. 2 times 2 times 2 is 8. If you pulled out your calculator and you did 8 to the power of bracket 1 divided by 3, close bracket, you would also get 2. Okay, and then here, what number times itself 3 times equals 27? It's 3. And if you did this on your calculator, you'd also get 3. Okay, so hopefully you're starting to see a pattern here. Okay, the cubed root of 64 is 4. And that is also 4. So hopefully you're starting to see a pattern that when you have a 3 here, or a cubed root, that the 3 in the denominator of your fraction, or the number in the denominator of your fraction, will also be 3. And it just has a 1 on top, a 1 in the numerator. Okay, so hopefully you're starting to see the pattern. So if I took the 4th root of let's say 16, the 4th root of 16, it would be the same thing as 16 to the power of 1 over 4. Okay, so right here. And by the way, let's write out our conclusion. So cubed root of a value is equivalent to that value raised to the power of 1/3. Okay. So you're probably wondering, where does the 1 come from, right? Like, where does the 1 in the numerator come from? Because we always end up getting 1 over, let's say, 2, or 1 over 3, or 1 over 4 as our fractions, right? So where does the 1 come from? And let me explain here where the 1 comes from. This 16 that's inside that root bracket, what exponent is above that 16, or belongs to that 16, that we don't write but that we know is there? So if I wrote the 4th root of 16, what exponent is on this 16 here? If you just see a number, you know that the exponent on it must be a 1. Okay, and that's where the 1 comes from. That's where the 1 comes from. So what happens is, when you convert this to a to a rational exponent, that 4 shoots down into the denominator below that 1 to get 16 to the power of 1 over 4. All right, we're just creating equivalent expressions here. That's all we're doing. So let's write out a rule. Okay, let's write out a rule. So if you have, so this is just going to be with variables. If you have a value, let's call it x, okay, and we took the nth root of that x, so whether it's a 2, a 3, or a 4, or a 5, 6, and so on and so on, okay, with a 1 as the exponent to that x, okay, that will become, as a rational exponent, this is our rule, x to the power of 1 over n. Okay, that's our rule. So what we're going to be doing is converting back and forth from rational exponents to radicals, and then back potentially to rational exponents. Okay, let's try some examples here. Okay, and actually, before we start, I do want to ask this to you. Are you able to take the square root of a negative number? That's my question to you. Can you take the square root of a negative number? So before we even start these examples, and I'm just going to write here. Okay, so can I take the square root, let's say, do I have to write the 2 here for square root? No. So let's say I take the square root of 81. Okay. I know that this ends up being 9, right? A number times itself 2 times equals 81. That's a 9. Can I take the square root of negative 81? Is that possible? Is there 2 numbers that multiply together to equal negative 9 or negative 81? Well, let's try. I know that I have to be working with 9s here, right? So 9 times 9, well, that's positive 81, right? But what about negative 9 times negative 9? That's also positive 81. So if I were to take 2 numbers, or if I were to take a number and multiply it by itself twice, I would find that I can never get a negative answer, because whether I use negative values or I use positive values, they'll always end up being positive in the end. So no, the answer is you cannot take the square root of a negative number. And the same applies for every even root. So for square root, okay, of negative 81, not possible. For the fourth root of negative 81, not possible. The sixth root of negative 81, not possible. So for every even root, it is not possible to take the root of a negative number. It just won't work. It just can't happen, right? Mathematically, you'll never get this to equal negative 81 or any of these to equal negative 81, okay? But if we can examine, instead of even roots, what about odd roots? So something like, and let me erase all this. Okay, so something like the cubed root of negative 27. Is that possible? Can you take the cubed root of a negative number? Okay, well, let's see. I know that I need to be working with threes here because I know 3 times itself 3 times will get me to 27. So let's see here. If I do 3 times 3 times 3, well, that equals positive 27. Okay, so that doesn't satisfy. I need it to equal negative 27. What if I do negative 3 times negative 3 times negative 3? What does that equal? Pull it out. You can pull out your calculator or you can do it in your head. Negative 3 times negative 3 is positive 9, right? And then times another negative 3. 9 times negative 3 is negative 27. So I can get an answer when I take the cubed root of a negative number. So if I take the cubed root of a negative number, I will get an actual value, in this case, negative 3. So the cubed root of negative 27. Now, it also applies for all the odd roots. Okay, all the odd roots, you can take roots of negative numbers for any odd root. For any of the evens, you cannot. All right, so that's important to understand going forward before we start all of these questions. All right, so remember that. Maybe we'll make a little note of it. So we can not take root of a negative number, negative value, if there is an even root. But oppositely, we can take the root of a negative value if there's an odd root. Okay, so numbers like 3, 5, 7, 9, 11, and so on and so on. Okay, so it says the instructions here, write in radical form, 100 to the power of 1/2. Okay, so let's write in radical form. Let's convert it to a radical, which means to have a root bracket. So I know I need to have a root bracket. My 100 will stay there. I suppose I can leave my 1 where it is. And what happens to my 2? It goes in that spot there. Now, do I have to write the 2 if I just put the root bracket? No. All right, it's understood that it means square root. So if I wanted to finish this off, I don't even have to put the 1 there. I can just put square root of 100. Okay. Let's take a look here. I know that I need a root bracket, and I know that I'm taking the root of negative 27. I know that there's a 1 here, so there's an exponent of 1 there. And the 3 will come out here. For this one, and I'm done. Like I don't need to, it doesn't say to evaluate, it just says to write in radical form, right? For this one, you see a decimal and you're probably feeling a little confused by that. But remember that 0.25, I'm hoping that you a lot of these decimals, I think in the textbook, they only do like 0.5, 0.25, or 0.75. Remember that 0.5 is 1/4, right? 0.5 is 1/2. 0.75 is 3/4. So those are like common fractions that you should remember, all right? That you should hopefully remember. So instead of 0.25, I'm just going to rewrite this as 1/44 to the power of 1/4 instead of 0.25. So now when I do the root bracket, it's easy. Keep my 1 here and put my 4 outside the bracket. Okay, so that's the 4th root. And it's important to note, I haven't explained this, this 4 is a little 4 that's inside. So it is not, I often get students do this. That is not how it is written, okay? So it is not like this. It's got to be a little 4 in the top corner of the root bracket. These mean totally different things. This means 4 times the square root of 144. This means the 4th root of 144. Totally different things. Okay, so please, do not write your 4s or these root values. Don't write them large in front of the bracket. You write them small in the corner. Okay? Okay, so what happens if, like, for example, in this question, you get something like this? So let me try this one. So remember that in the previous questions, all we saw was, like, let's say the cube root of -216. There was no exponent on the outside here. So we assume that the exponent was a 1. Okay? Well, in this case now, the exponent is actually a 5. And nothing changes. All right? Absolutely nothing changes. You do the exact same thing. So this is asking us to write in exponent form. So we're going to convert this back to a rational exponent. So you're going to do -216 to the power of, keep the 5 in the numerator, and bring the 3 down into the denominator. So it becomes -216 to the power of 5/3. Okay? So let's write a rule for that. All right, let's write a rule. So if you have the nth root of a value, okay, raised to the power of something, okay, like m, nothing changes, all right? This is just a different, it's the same rule, essentially. It's just that before, my m values were always 1. Now they're actually going to be different numbers. So you're actually going to get x to the power of, the n goes into the denominator. So it's x to the power of m divided by n. All right, you don't have to memorize that. You just have to remember that the n just shoots down into the denominator there. Okay? All right, so let's try this question. So this question actually goes back to our first example, right? And remember, if you don't see a exponent here, it means that it's a 1. So this just stays 64 to the power of 1/5 as a rational exponent. This one I already did. Okay. And now this one becomes, this 2 shoots down into the denominator. It becomes 121 to the power of 2/2. Now, this is a fraction we can reduce. We don't want to leave it as 2/2. What's 2 divided by 2? 1. So it's really 121 to the power of 1, which is just 121. Okay? So nothing overly difficult right now. All we're doing is going back and forth between radicals and rational exponents. So we're converting back and forth. Okay, that's all we've learned so far. In this next series of questions here, these last 4 questions, we're going to be asked to write as a single power and then evaluate. And we're going to do our best to evaluate without a calculator. Okay, so without a calculator. So let's write this as a single power first. We have the same base, we have 2 8s here, and we're dividing the same base. So back to our exponent laws, what can we do with the fractions? Okay, write it as a single 8 and then subtract the exponents. So 2/3 minus 1/3. Okay, we're dividing the same base so you can subtract the exponents. What does that end up equaling? What's 2/3 minus 1/3? Well, they're already common denominators, so we can just subtract 2 minus 1, and we get 1/3. Now we have to evaluate, and I have no clue what 8 to the power of 1 over 3 is without a calculator, right? But if I convert this to a radical, meaning I take the cubed root of 8 to the power of 1, I can figure out what number times itself 3 times equals 8. It's 2. 2 times 2 times 2 equals 8. So my answer here, my evaluation, the answer is 2. And I didn't even have to use my calculator because this radical was simple enough that I can do that in my head. Okay, so we're going to do our best. In this next question, you'll see that we have to use a calculator because it just gets way too difficult. But for the most part, I'm going to ask that you try to do it without one. This next question is challenging only because it requires you to remember how to add and subtract fractions that don't have common denominators. Because as you can see here, we have all common bases of 10, right? So this is 10 to the power of negative 4 over 5 times 10 to the power of 1 over 15. So if you're multiplying the same base, you can add the exponents. So write it as a single power. But then it's divided by 10 to the power of 2 over 3. Well, I know that then all I need to do then, if this is divided by, all I need to do is subtract, because when you're dividing, the exponent law says to subtract the exponents. All I need to do then is subtract 2 over 3. Okay, so I can do that all in one line. If you want to break it up as 2 separate steps, you certainly can. So what I suggest you do is you go off to the side and you work out what this fraction would be. So negative 4 over, so this is just my work off to the side. Negative 4 over 5 plus 1 over 15 minus 2/3. What's my common denominator? 15. So I need all of these fractions to have a 15 below. Well, this one was already 15, so it stays as 1 over 15. This one, to go from 5 to 15, we multiplied by 3. Whatever you do to the bottom or to the denominator, do to the top or to the numerator. So negative 4 times 3 is negative 12. Here, to go from 3 to 15, we multiplied by 5. Whatever you do to the bottom, do to the top. 2 times 5 is 10. Now I can add and subtract straight across the top. So I know my answer is going to have a denominator of 15. And let me just clean this up a bit. So I know my answer is going to have a denominator of 15. Now what's negative 12 plus 1? That's negative 11. Minus 10 is negative 21. So this is why I said, like, this question is just bizarre, but it helps us work on our fraction skills, and that's why I chose it. So the answer to this, and we can reduce this fraction if we divide top and bottom by 3. We can reduce that. So that actually equals negative 7 over 5. So we end up getting this weird fraction here, but we can convert this to a radical. Okay. First off, it is a negative exponent. So you know what I'm going to do? I'm going to flip it so that it is a positive exponent. Okay, negative 7 over 5 is a negative exponent. Flip it to the bottom, you get 7 over 5 that's positive. and I bring the 10 with it, leaving behind a 1 in the numerator. Now, I'm just going to put my answer right here. I'm going to convert this to a radical. So I'm going to do 1 over, and instead of 10 to the power of 7 over 5, I'm going to take the 5th root of 10 to the power of 7. Okay? We can't solve that in our head. Let's just keep it like that. So we didn't evaluate this answer, but it was a good question that helped us write this as a single power. We did write it as a single power here. And then we converted it to a radical to be 1 divided by, or 1 over, the 5th root of 10 to the power of 7. Okay? Okay. Now, these next two are a little bit more challenging. You can see we don't have the same base here, right? We don't have the same base. So we can't, that's a 27, that's an 81. We cannot do anything with these exponents. Plus, we're not multiplying or dividing, we're actually subtracting. There's no exponent laws for this. There's no exponent laws for subtracting here, right? Or adding. The exponent laws are only for multiplying and dividing. That's all they work for. All right? So let's see how to go about to do this. I mean, you might be stuck at this point thinking, okay, what the heck am I doing next? Well, it says to evaluate. So what we're going to do is see if we can evaluate this in our heads without a calculator by converting them to radicals. Because I have no idea what 27 to the power of 2 over 3 is just looking at it like that. But if I shoot the 3 out and I take the cubed root of 27 and I square that, I might be able to find that answer without using a calculator. All right, and then bring down the minus sign and do the exact same thing here. Take the 4th root of 81, and then that 3 stays where it is out there. So let's see. What is the 3rd root of 27? What number times itself 3 times equals 27? It's 3. Don't forget the squared. It's still there, the squared. Minus, what is the 4th root of 81? What number times itself 4 times equals 81? You may have to play around with your calculator here or some of your multiplications. It's actually 3 again. 3 times itself 4 times equals 81. And don't forget the cubed. It's still there. Now, you see, I didn't really use my calculator. And I know what 3 squared is. It's 9. I know what 3 cubed is. So I bring down the minus sign. I know what 3 cubed is. It's 27. So 9 minus 27 is actually negative 18. So I was able to calculate this, even though when I just looked at this, there was no way I could calculate that in my head, right? I have no idea what those are. But when I converted them to radicals, it became more apparent to me that I can solve this without even using a calculator. Okay, so you could see that before calculators were invented, this was a handy way of doing math, right? It was a lot quicker and easier to do this way. Let's do this final question. All right. Again, these are all pluses and minuses, so there's no exponent laws that apply to this. It has to be multiplication or division for exponent laws to apply. All right, so we just have to take each one of these values, convert them to radicals, and see if we can solve them or evaluate them without a calculator. So 81 to the power of a half becomes the square root of 81 to the power of 1. This one's already a radical, so plus the cubed root of 8, so that's nice. That's already done for us. Minus, bring down that minus sign, the 5th root of 32 to the power of 4. Right, the 4 stays in the exponent position when the 5 shoots outside the radical or the root bracket. Plus the 4th root of 16 to the power of 3. Okay, so let's see if we can figure these out without a calculator. Square root of 81, I know, is 9. Okay, and it's just 9 to the power of 1, which I know will just be, I'll write to the power of 1 there, but I'm just doing it to show all my work to help explain it. What number times itself 3 times equals 8? 2. Bring down the minus sign. What number times itself 5 times equals 32? 2. Except this time it's a 2, but look what's still out there that we haven't done. The exponent for. All right, so make sure you bring that down. Don't forget about that. Plus, the 4th root of 16. What number times itself 4 times equals 16? It's also 2. Just don't forget that the cubed is still there. So bring down that to the power of 3. So we end up getting 9 plus 2 minus, what's 2 to the power of 4? 16. Plus 2 to the power of 3, 8. Look at that. We were able to solve this. I know that, it seems easy, but you just really need to practice this over and over again. But we were able to solve this without even pulling out our calculators. So we have 9 plus 2 is 11, minus 16 plus 8, end up getting 3. Okay, so that concludes this lesson. And if we're recapping, we converted back and forth between exponential, rational exponents, and radicals. The reason being is because when we convert a rational exponent to a radical, we find that it's easier to evaluate or solve without a calculator. Okay, that is the reason for it. So that concludes the entirety of lesson 1.